Okay, you all welcome to the workshop technology subject. We are discussing metal cutting theory. Okay, today also we are continuing with this topic. Last class we discussed force relationship in orthogonal metal cutting operations. We are discussing in the first year level. We are discussing only the orthogonal metal cutting operations. Orthogonal mean in orthogonal metal cutting operations. Only in orthogonal metal cutting operation we can represent all the velocity vectors and the force vectors on two-dimensional plane. Okay, the analysis is very easy in orthogonal metal cutting operations. Okay, then last class force relationship we discussed, and also in a previous class we discussed velocity relationship in orthogonal metal cutting operation. I gave some videos also with the last lecture. I think you all the more clear with this up to now, okay, about this metal cutting theory, so on. So that today also we are continuing with this topic. Today we first I am going to give some theory about this orthogonal metal cutting operation. Then later we are going to discuss some past paper questions regarding to this topic. Okay, each year you will get you are getting the one question from this metal cutting theory for your exam. So then we are discussing these past paper questions today. Okay, let's continue to the today's discussion. Okay, today we are going to discuss first we are going to discuss the material removal rate. Material okay, the first today we are going to discuss about the material removal rate in machining. What is the material removal rate in machining? Okay, this is we are giving the material removal rate, MMR in machining. MMR in machining, material removal rate. So what is the material removal rate? Okay, it is measured in the units, the cubic meter per second. Okay, cubic meter per minute. Okay, the cubic inches per minute. This kind of units are used to measure the material removal rate in machine operations. So material removal rate mean in machining the volume of material removed per unit time is called material removal rate. Okay, in machining the amount of volume removed from the workpiece in a unit time is called material removal rate. Okay, let's take for example, let's take the orthogonal metal cutting operation. Okay, let's take the orthogonal metal cutting operation. Okay, then let's take the orthogonal metal cutting operation. Yeah, orthogonal metal cutting operation. This is the workpiece. Then this is the cutting tool. So the workpiece. Let's take this kind of layer going to be removed using the cutting tool. Okay, let's take this is the cutting tool. Okay. This is the cutting tool we are used. Okay, this is the width of the cutting tool. You can see. Okay. This is the cutting tool. Using this cutting tool, we are going to remove this kind of groove from the workpiece. and this is the removing chip. This is the removing chip from the workpiece. Okay, that means this kind of groove we are going to remove. This kind of groove we are going to remove from the workpiece. This is the groove we are going to machine in this operation. This kind of groove we are going to generate. Okay, in this process, let's take the tool is moving with the velocity v, the cutting velocity. Let's take the vc, the cutting velocity v. Let's take the depth of cut. Depth of cut means this depth. Let's take it as the d. Okay, then width of cut. Width of cut means this dimension, the width of cut. Okay, d mean depth of cut, depth of cut. W mean width of cut, width of cut. The vc mean cutting velocity, cutting velocity. Okay, cutting velocity. Then vc mean the cutting velocity. Okay. Then this kind of groove are going to be removed from the workpiece. Okay, then we are going to find what is the rate of material removal in this process. What is the rate of material removal in this process? Then how to find the material removal rate? Okay, let's take the vc in meters per minute. Okay, meters per minute. Then let's take these in d and w are in inches, unit in inches. Okay, okay. Then we are going to find what is the volume of material removed from the workpiece in a unit time. Okay, in a 1 minute time, what is the tool travel? In 1 minute time, what is the tool travel? Let's take this one also inches. Yeah, sorry, the cutting velocity given in inches per minute. Okay, then we can easy for this calculation, inches per minute. So then what is it per 1 minute? If you take the 1 minute time, what is the tool travel? It is equal to vc. Okay, it is equal to vc. Let's take in a 1 minute period. In 1 minute period, it comes to this kind of position. Okay, then how to find the, that mean in a 1 minute period, that mean in 1 minute period this much of volume, that mean this much of volume removed from the workpiece. What is the volume of this removing volume? So what is this cross section? That is equal to d into w, because depth is d, this one is w. Okay, so what is the volume removed in 1 minute? Volume removed in 1 minute, then we can easily find what is the volume? d into w into vc, d into w into vc. That is called, the volume removed in 1 minute is called material removal rate. Material removal rate. So then you can write the material removal rate is equal vc d into w, the cubic inches per minute. Cubic inches per minute. Okay, cubic inches per minute. I think this one calculation is very clear to you. The material removal rate means the volume of material removed from the workpiece. Okay, volume of material removed from the workpiece in a unit time is called material removal rate. This calculation is very important. Why this calculation is very important? when we are going to estimate the total time taken to manufacture certain component in machine operation, we should know what is the material removal rate. For certain machine operation, if we know the material removal rate, in other way, we can calculate, we can estimate what is the total time taken to manufacture certain geometric shape. Okay, that is very important to estimate the production rate, profit, and the labor cost, and also the energy consumption. That is very important. Okay, this calculation is very important to estimate these things. Okay, then this is the in generally this is the material removal rate in simple machine operation, but according to the type of machining, it may vary. For example, the turning operation, we are getting the another equation. If it is a milling operation, we are getting the separate equation. So then in generally this is the equation for material removal rate. Okay, let's take the another example for the material removal rate in turning operation. Okay, turning operation. Okay, material removal rate in lathe turning operation. Okay, let's derive an expression for this operation, material removal rate in orthogonal turning operation. Okay, let's take this is the workpiece we are going to consider. Okay, turning operation. Okay, you already know this what is meant by the turning operation done on the lathe machine. You have seen the plenty of videos regarding to this turning operation. Okay, you know about this turning operation. Okay, in turning operation you used to reduce the diameter of a workpiece. Okay, to reduce the diameter of the workpiece, the cutter rotate against the cutting tool with, let's take this velocity, let's take it as rotation velocity, let's take it as n in rpm, revolutions per minute. That means in 1 minute period it produces n number of revolutions. Let's take the diameter, let's take the diameter as capital D. Then let's take the depth of cut is D. Then comparing to this simple d is very small comparing to the capital D. Okay, this is one of the assumption for this calculation. This simple d is very small compared to the capital D. That means the shaft dimension, this depth of cut is very small. Okay, then the feed rate, the F, let's take F inches per revolution, F inches per revolution, D also in inches, then in rpm, the D also, this capital D also in inches. Okay, let's take, this is the, you already know these things, the cutting tool, this is called the workpiece, this is the rotating axis of the workpiece. In turning operation, you know, the cutter feed parallel to the rotating axis of the workpiece. Okay, this is the rotating axis of the workpiece, cutter feed parallel to the rotating axis of the workpiece in a turning operation, in order to reduce the diameter of the workpiece. Okay, this is 5D. Okay, diameter. Then let's take this obtained diameter 5D dash. Okay, then in this operation we are going to calculate the material removal rate. Okay, material removal rate for this. Okay, then if you take the 1 minute period, okay, same as in previous, we are going to consider the 1 minute period. Okay, 1 minute period. In a 1 minute, if you take the 1 minute, what is the tool travel? What is the tool travel in 1 minute? In 1 minute, let's take the tool travel. In 1 minute period, what is the tool travel? Okay. Here, per one revolution, what is the tool travel? Per one revolution, the tool travel is F in inches. Okay, per one revolution, tool travel is equal F in inches. So how many revolutions per minute? N. So for n revolutions, what is the tool travel? F into n. F into n. Okay. So then per 1 minute, what is the number of revolutions? N. So 1 minute tool travel is equal to F into n inches. F into n inches. Okay. I think you all more clear with this one, no? Okay. F into inches. So then I will draw that one. The tool will come to this kind of position after a 1 minute period. Tool will come to this kind of position after 1 minute period. After 1 minute period, tool will comes to this kind of position. Okay. Okay. Then you can see what is the volume of material removed in this 1 minute period. You can see this kind of ring shape volume removed from the workpiece. This kind of ring shape volume is removed. This kind of ring shape volume is removed from the workpiece, no? Okay. This kind of the in both sides the diameter reduced in both sides. Okay. Okay. This kind of ring shape volume is removed. So if you take the cross section, what is this area? I am asking this area. What is this area? What is this area? First tell me what is the length. The length is equal F into N. F into N. Okay, F into N. So what is the thickness of this? What is the thickness? This thickness is equal to D. Is equal to D. So what is this area? This area, this highlighted area, yellow color, F N into D. Okay, inches into square. Okay. Okay. So then how to find the total volume? How to find the total volume? Okay, we have to use the Pappus theorem. I think you may heard the Pappus theorem in maths. To find the volume, we are using the Pappus theorem. So what is the circumferential length? What is the circumferential length? What is the circumferential length? Is equal to 5 into D, no? 5 into D. So then that's why I made the first assumption. The D is very small compared to the simple D is very small compared to the capital D. So you can calculate the outer surface circumferential length. Okay, that's not affected to the calculation. Okay, because the simple D is very small compared to the capital D. So that this circumferential length is equal 5 into D. So then the total volume removed in 1 minute is the volume of this ring shape part. The volume removed, in 1 minute is equal this cross-sectional area F n into D into this length, circumferential length, 5 into D. Okay. So that means in orthogonal machining operation, we can derive an expression for the material removal rate. Material removal rate is equal, okay, F n D 5 into capital D. Okay. Then in here, what is mean by this multiplication of these three terms? N 5D. Okay. In the previous lectures we discussed the multiplication of these three terms, that is equal to cutting velocity, no? That means the surface velocity of this shaft is the cutting velocity, 5dn. So instead of this multiplication of these three terms, we can put the Vc. That means the material removal rate is equal VFD. Okay, simple D. Material removal rate is equal VF simple D for turn-in operation. Okay. V mean cutting velocity. The V mean the cutting velocity. F mean the feed rate. Okay, it's not speed, it's a rate. Feed rate. The D depth of cut. Okay. If these all these are measured in unit in inches, let's take this is measured in inches per minute. If this is inches per revolution, then this is the D in inches. So then we are getting the units cubic inches per minute. Okay, cubic inches per minute for material removal rate. Okay, this is how we are calculating the material removal rate in turn-in operation. Okay, then generally this is how we are calculating the material removal rate. Generally we are calculating in this way. According to the application, you should be able to find the material removal rate in machining operation. So knowing this material removal rate is very important. For example, we are producing this kind of let's assume in our machine shop we are producing this kind of work pieces. We want to manufacture 10,000 items. Okay, then we want to estimate the manufacturing cost for this part. Okay, when you are going to estimate the manufacturing cost for this part, that is very important, knowing material removal rate. Without knowing the material removal rate, we can't calculate machining time for certain component. Okay, so then we can't estimate the labor cost, we can't estimate the machining energy required. Okay, machining energy required. So that this calculation is very important in those who are doing the if you going to work on this relating to this kind of machining operations on industry, you will definitely doing this calculation to find the to estimate the production time. This calculation. Okay, this is very important calculation. Okay, then next we are going to calculate machining power in orthogonal machining operations. Okay, let's move to that topic. Okay, then next theory part is power consumption in orthogonal metal cutting operation. Okay, for any orthogonal metal cutting operation, we can draw this kind of diagram indicating these parameters. Is the workpiece. Okay, for any orthogonal metal cutting operation, we can draw this kind of diagram. Okay. This is called the cutting tool. Cutting tool, the workpiece. Workpiece. This is called the removing chip. Metal chip. Okay. Let's take this tool is moving with the velocity in this direction. The VC, cutting velocity. Okay. Cutting velocity. Okay. So what are the forces we are applying for this metal cutting operation? What are the forces we are applying for this metal cutting operation? In the last lecture we discussed in detail about this forces. We have derived equation. We derive equation for force relationship also. You know now. So what are these two forces we are applying for this cutting operation? This is called Ft. This is called Fc. This is called cutting force. This is called thrust force. Okay. Then you can see in this diagram, only in this direction the tool is moving. Okay. So only this component of this force is doing the work. So what is the work? The work, in simply we can say the work is equal force into distance travel. No, in simple way you can say the force into distance travel. Okay, force into distance along that force vector direction. Okay. F dot is called work. So in here, in your A level also you are learning the power is equal F distance travel divided by time taken for that distance travel. Okay, time taken for that distance travel. Then the power is equal F into velocity. In here, what is the power consumption? So in that way you can derive an expression for the power consumption. Only this component consumes the power. Okay. So what is the power consumption? Power consumption is equal Fc into Vc. Okay, this is the power consumption in orthogonal machine operations. Okay, orthogonal machine operations. Power consumption in orthogonal machine operations. Force into velocity. Okay, force into velocity. Power consumption means the energy consumed in unit time is called power. Okay, energy consumed in unit time is called power. So this is the power consumption in orthogonal machine. This is how we are calculating power consumption. Okay, now you know how to calculate power consumption in material in machining. Okay, so then next topic is specific energy of material removal. Okay, specific energy of material removal means to remove unit volume of material from the workpiece. What is the energy consumption? To remove unit volume of material is called specific energy of material removal. Okay, specific energy of material removal, that joules per cubic meters. Okay, joules per cubic meter, the unit for joules per cubic meter, or joules per cubic inches. Okay, joules per cubic inches, the joules per cubic millimeter. These are the units for to express the specific energy of material removal. Okay, now you know how to calculate the energy consumption in machine operation, and also you know how to calculate the material removal rate. Okay, so then specific energy of material removal. Specific energy of material removal is equal, okay, total energy divided by volume of material removed. Volume of material removed. Total volume of material removed. Okay, the volume of material removed. Okay, then what is for the total energy? Total energy, power into time, machining time. Power into machining time. Okay, power into machining time. Okay, then what is the volume of material removed in entire machining process? The material removal rate into time. Okay, this is energy for total machining. That means the power into time, total energy we are getting. Then the material removal rate, we are getting the cubic inches per minute or something. Then if we multiply by the T, total machining time, then we are getting the total material removed per in a T time. So then we can cut this the T common term. So then we are getting the answer, the P divided by material removal rate. What it means, what we are getting here, the power machining power divided by the material removal rate. Okay, then we are getting the specific energy of material removal. So keep remember, then when we are dividing this one should be a same unit for time measurement. Okay, same unit for time measurement. Then we are getting that we can get this ratio. For example, if this is, we are measuring joules per cubic inches. The machining power, that means joules per second. Okay, the material removal rate also should be cubic inches per second. The time unit should be same. So then we are getting units, joules per cubic inches, like that. Okay, joules per cubic inches, like that. If this one is not, we have to convert into a one same time units. Okay, second or minute. This is how we are calculating the specific energy of material removed. Same as if we know the specific energy of material removal, we can estimate what is the total energy consumption for certain machine operation to obtain certain geometry for the workpiece. Okay, if your initial geometry is known, okay, initial geometry of the workpiece is known, then the obtained geometry also known, then we can estimate that this much of volume has to remove. Okay, then we can estimate the energy required for this machine operation. Okay, the energy required for this machine operation is known, means we can estimate the cost per energy. Okay, that is very important calculation when you are going to estimate the profit, when you are going to estimate the cost per part. That is very important calculation. Okay. These are the things we are going to discuss under this metal cutting theory. Okay, then in last 4 lectures we discussed this metal cutting theory. This is all about the theory of this first topic. So then today we are going to discuss some the past paper questions regarding this discussions. Okay, metal cutting. Okay, let's move to the past paper questions. Okay. Okay, this is the 2018 paper question regarding this question 1, the part C. Question 1, part C. In an orthogonal turn-in operation, the following data were obtained. Okay, following data were obtained for the orthogonal turn-in operation. Chip thickness is equal 0.45 millimeters. Depth of cut 3 millimeter. Width of cut 2.5 millimeter. Feed rate given 0.25 millimeter per revolution. Cutting force is given 1130 Newton. Thrust force 295 Newton. The cutting speed 150 meters per minute. Then the rake angle also given the plus 10 degree. So they determine the followings. Determine the followings. The chip thickness ratio, shear angle, velocity of chip along the tool face. Okay, these are the things they have to determine. Okay. Then first one is very few. Okay, this is the question. In 2018 paper. So let's see how to solve this question. Very simple one. Very simple one. Okay. First we have to calculate the chip thickness ratio. Okay. Then let's see how to solve this problem. Okay. First one, the 2018, the Q1 part C. First one, chip thickness ratio R. R is equal what is R? T1 divided by T2. That means undeformed chip thickness divided by the chip thickness. Okay, here the depth of cut, undeformed chip thickness is equal to the depth of cut. Depth of cut divided by chip thickness. Chip thickness, that is equal to depth of cut is equal to 0.3. Then chip thickness 0.45. Then we are getting the answer 0.3 divided by 0.45, 0.667. This is the chip. Okay. Here the R, we are getting the answer for the R is equal to 0.667. Then the second part, the problem is asking to find the shear angle. Shear angle, the 5 is equal tan inverse R cos alpha divided by 1 minus R sin alpha. This equation we derive in last class. In previous class we obtained this expression. I think you are familiar with this expression. So then R means the chip thickness ratio, alpha means the rake angle. Then we are getting the 5 shear plane angle. Then the 5 is equal the tan inverse, what is R, 0.667 cos alpha. Alpha is given cos 10 degree, 1 minus R, so 0.667 sin 10 degree. Okay, so what is the value we are getting? Let me calculate the value. Okay, the tan inverse shift tan inverse, 36.61 degree. This is the answer we are getting the shear for the shear plane angle. Okay, please check this answer. Okay, let me check it again. Okay, 36.61 degree. Okay, 36.61 degree. Then the problem also asking to find the velocity of the chip along the tool face. In the last in the previous lecture we discussed the velocity relationship in orthogonal metal cutting operation. So what is the velocity along what is the equation we have derived to obtain the velocity relationship in orthogonal machining? The velocity of the chip along the tool face, that means the VF, chip flowing velocity, the VF we have with the equation VF is equal VC sin 5 divided by cos 5 minus alpha. This is the equation we derive for the chip flowing velocity, that means the velocity of the chip along the tool face. That means in orthogonal machining, okay, in orthogonal machining, this velocity is called chip flowing velocity. Okay, this velocity, the VF, okay, VF, that means the velocity of the chip with respect to the tool face is called chip flowing velocity. In the previous lectures we obtained this expression, so then we have all the data, just only substitute this data on this equation. Okay, what is VC? VC is given VC, the cutting speed is given the 150 meters per minute, 150 meters per minute, the meters per minute. Then answer also we are getting meters per minute. So what is the sin 5? Sin 36.61 degree divided by cos 36.61 minus alpha rectangle. So rectangle also given that 10 degree. Okay. So for the VF we are getting the answer. For the VF we are getting the answer. Hundred, yeah, 100 units meters per minute. 100 meters per minute. This is the value we are getting for the chip flow velocity along the tool face. Okay, please check these answers. Do it at home and please check these answers. Okay, this is how we are doing this. This is how we are doing this calculation. The 2018 paper, past paper. The chip thickness ratio. This is how we are finding the ratio. Then the shear plane angle. We have the equation to find the shear plane angle. We can't measure the shear plane angle, only we can mathematically determine. Okay, then chip flowing velocity we are calculating in this way. Okay, this is the 2018 paper discussion. Okay, then let's move to the 2019 paper. 2019 paper. Okay, 2019 paper. Okay. Okay, this is the 2019 paper. The mostly similar question. 2019. Okay, in an orthogonal turning operation, the following data were obtained. Spindle RPM also given. Spindle RPM is given, and also the workpiece diameter also given. Then chip thickness, chip length is given. So instead of chip thickness, here it is given the chip length. Length of cut also given. Depth of cut also given. Width of cut also given. The feed rate is given. The cutting force is given. Thrust force is given. Rake angle given. They determine the followings. Chip thickness ratio, shear angle, velocity of the chip along the tool face, shear force, friction coefficient, material removal rate, and specific energy of material removal. Okay, so then let's see how to solve this problem. Okay, first one, the chip thickness ratio. Okay, in this time the thickness of the chip is not given. You can see thickness of the chip data is not given, so in that way you have to calculate it from the by equating the volume. Then you will get the okay. In here in a 2019 paper, the chip thickness is not given. In that way we have to find the chip thickness ratio by equating the volume. The volume removed is equal to the volume in the workpiece before it removed. So then the first one, chip thickness ratio, the R is equal. So R we are going to find. First I will draw the diagram for this one. Okay, this is the orthogonal machine operation. Let's take. Then let's take this is the cutting tool. Okay, then this length is given. The chip length is given. This chip length 32 centimeters. Then before it remove from the workpiece, the length of cut also given. Length of cut is like greater than this value is 75. Anyhow, before it remove and after it remove, the volume should be same. Okay, so what is the volume after it remove? 32 into length of the chip into cross section. The width doesn't change in orthogonal machining. W. Let's take this the chip thickness. thickness is equal to the 75 into W into depth of cut. Okay, W into depth of cut. Depth of cut. Okay, depth of cut. W into depth of cut. Okay, then chip thickness ratio, then we can cut easily the W. Then by taking the ratio, okay, we are getting 32 divided by 75 is equal depth of cut divided by chip thickness, that is equal to R. Then R is equal 32 divided by 75, 0.42, so I am going to add it to a 427. Okay, this is the chip thickness ratio we are getting. Okay, then the secondly, the problem is asking to find the shear angle. Okay, second part, the problem is asking to find the shear angle. We have an equation to derive this shear angle. Phi is equal tan inverse R cos alpha 1 minus R sin alpha. Here the equation to derive the shear plane angle. Okay, this is the equation to derive the shear plane angle. In here, what is okay, 5 is equal tan inverse, what is R? 0.427 cos alpha, right angle also given the 10 divided by 1 minus 0.427 sine into 10. Okay, okay, so then let me take the answer. Uh, 0.454, that means the 24.43. I am getting the 24.43. Therefore, the 5 I am getting 24.43 degree. Okay, this is the chip thickness ratio and this is the shear plane angle we are calculating. Okay, then problem is asking in the third part, velocity of the chip around the tool face. Okay, VF. Okay, VF is asking. VF is asking. Okay, we have the data 5 is equal 24.43 degree. Then we are going to calculate chip flowing velocity. Third part. Chip flowing velocity. We have an equation to derive this chip flowing velocity. Vf is equal Vc. What is that equation? Vc sin 5 divided by cos 5 minus alpha. Okay, this is the equation. Okay, then the problem is Vc is unknown. How to calculate the Vc? Okay, how to calculate the Vc? Here the two data given to calculate the Vc. The workpiece diameter is given, spindle RPM also given. Then the Vc is equal 5 dn. Okay, first lecture we discussed this calculation of this one. What is 5? 5d. What is d? Workpiece diameter in millimeters into n. RPM 900. Okay, then we are getting the answer for this VC is equal to 60 into 900, that is equal to 169.65 meters per minute. Okay, meters per minute. This is the answer I am getting. Meters per minute. Okay, then we can find the VF. 169.65 into sine 5, 24.43, cos 5 minus alpha. What is 5? 24.43 minus alpha. Alpha means rectangle 10 degree. Okay, then VF. What is the VF? Here it is. Okay, so let me find the VF. 169.65 into sine 23 divided by 72.45 meters per minute. Meters per minute. Okay, please check this answer again. Okay, this is the answer we are getting for the chip flowing velocity. Okay, then next one, shear force. The fourth question is to find the shear force. The fourth question is find to shear force. So how to calculate the shear force? In the last lecture we obtained the equation to calculate the shear force. We derived an expression to calculate the shear force. What is that? The V shear force, Fs is equal, last class we derived this equation. Shear force Fs is equal R cos 5 plus lambda minus alpha. This is the shear force. But in here lambda is unknown. Lambda means the friction angle. First we have to calculate the mu to find the lambda. Okay, what is the equation for to calculate the mu? Ft cos alpha plus Fc sin alpha divided by Fc cos alpha minus Ft sin alpha. This is the equation to obtain the mu. Okay, let me obtain this mu. Mu is equal, Ft is given, thrust force is given. What is the thrust force? Is given 752 cos 10 degree minus Fc cutting force 1130, again sin into 10 divided by Fc cutting force 1130 cos 10 degree minus Ft 752 752 into sine into 10. Okay. Then we can calculate the mu. Okay, let me obtain the expression for the mu. Sorry, this one is plus. This one is plus. So then we are getting the answer for the mu is equal 0.95354. Sorry. Either for the mu, then we can calculate the lambda. Tan inverse mu is equal lambda 43.64 is the lambda. Okay. Now we are having these values, then we can calculate the shear force. Okay, for the Fs we can calculate the force part. Fs is equal, what is this is the r cos 5 minus 5 plus lambda minus alpha. Then lambda we have obtained. The Fs is, what is r? R mean ft square plus fc square root is called r cos 5 plus lambda minus alpha. Then Fs is equal, what is ft? Plus force 752 into square plus the Fc cutting force is equal 30 into square root cos 5. What is 5? 5 we have obtained the equation that 24.43 plus lambda we have obtained 43.64 43.64 minus alpha 10 degree. So then we can obtain the phase shear force. Okay, then Fs, for the Fs we are getting answer 717.88 Newton. Okay, please check this answer. This is the answer we are getting for the shear force. Okay, shear force. The shear force mean in orthogonal metal cutting, the shear force mean the shear force mean if we can separate this chip and the workpiece along the shear plane, what is the resistance to move this chip along this shear plane is called shear force. Okay, shear force. Okay, then let's move to the the shear force. We have derived the friction coefficient. Actually this we have already calculated the friction coefficient. What is the friction coefficient? That is equal to 0.954. So then you can put that answer for that one. Actually this one should be comes to this position. Okay, then the material removal rate. Now we are going to calculate the material removal rate. Question 6. Okay, next we are going to calculate the material removal rate. That means sixth question, material removal rate in machining this turning operation. This is the orthogonal turning operation. Okay, just take, I will figure out this problem. Okay, this is the workpiece. It's rotating in this way. I will do the cutting tool also. Okay, this is the cutting tool, is moving in this direction. The feed rate then okay, then material removal rate. What is the material removal rate? Material removal rate means the volume of material removed per unit time. Volume of material removed per unit time is called material removal rate. So let's take, I am taking the 1 minute. Okay, 1 minute. Okay, 1 minute. What is the, in 1 minute, what is the tool travel? In 1 minute, what is the tool travel? Let's take the tool is, let's assume the tool is coming to this kind of position after 1 minute. Okay, then this much of the, this is the length, this is the volume removed in a 1 minute period. So what is this length? This length L is equal, in 1 minute tool travel is equal, okay, in 1 minute tool travel is equal, okay, then per revolution feed is 0.5 millimeter, 0.5. Then how many revolutions per 1 minute? 900. Okay, per 1 minute this is the tool travel in millimeters. Okay, 0.5 into 900, that means 450 millimeters. 450 millimeters, that means tool, this length is equal 450 millimeters per in 1 minute period. Okay, then what is the volume? First, what is this? D is equal, there is given depth of cut is given 0.45. Okay, 0.45 millimeters. Okay, 0.45 millimeters. Then this depth also given, length also given. Then circumferential length. What is circumferential length? That is equal to 5d. No, 5d. Circumferential length is equal to 5d. What is 5? Sorry, 5 diameter is d. 5 into 60. So then material removal rate in 1 minute. Material removal rate for 1 minute is equal circumferential length. That means this kind of ring shape volume is removed in this process. Okay, this kind of ring shape volume is removed in this process. So that ring shape length is equal into 5 into d in millimeters into this length 450 into this thickness 0.45. Then we are getting the answer cubic millimeter per minute. Cubic millimeter per minute. Material removal rate is equal cubic millimeter per minute. That is equal we are getting the answer 38,170.35 cubic millimeter per, okay, cubic millimeter per minute. Okay, this is the answer we are getting for this in a, that what it means, in a 1 minute period this much of volume removed from the workpiece, this much of volume removed from the workpiece. Okay, okay, 5d 0.5 into 900 rpm 450. Okay. This is the volume of material removed per unit time. Then the last question, last question 7, specific power of material removal. Specific energy of material removal. Of that is equal, we have derived an equation for this one. The specific energy of material removed, the power for machining power, divided by material removal rate. Okay, what is meant by the machining power? Fc into Vc. Fc into Vc is called machining power. Okay, Fc into Vc is called machining power. Material removal, already we have obtained the equation for the material removal rate. Okay, then for this one I am going to calculate the energy per 1 minute. Energy per 1 minute. So what is the cutting force? Fc, then energy per 1 minute. The cutting speed also we calculated the cutting speed in the previously. What is the cutting speed we obtained? Okay, Fc, then I'm going to convert this power into watt. Then we can see the cutting speed. For the Vc we are getting 169.65 divided by 60 meters per second. Okay, meters per second. Then Fc into Vc divided by material removal rate. So then Fc, what is Fc? So cutting force 1130 into Vc 169.65 divided by 60. This is the power consumption per, this is the power actually, that means energy consumption per 1 second. Energy consumption per 1 second. So what is the material removal rate per 1 second? 38,070 into 35. Here this is the value for the cubic millimeter per minute. So cubic millimeter per second we have to divide it to a 60. Okay, 60. So then specific power we can calculate. Okay, we can cut these values, then we are getting the specific power. Specific power, what is the unit? Here we are taking the joules per cubic millimeter. Joules per cubic millimeter into I am getting this answer 5.022 joules per cubic millimeter. Okay, this is the answer I am getting. Please check this answer. So then let me check it again. Yeah, this is the answer we are getting. The 5.022 joules per cubic millimeter. What it means? To remove cubic millimeter, from the workpiece, we need this much of energy. Okay, to remove this 1 cubic millimeter from the workpiece, we need this much of energy. So if we know the geometry we should obtain from the workpiece, let's say this is the initial workpiece shape. Okay, let's take this is the 5 in diameter. Then let's take this is the shape we are going to manufacture. Okay, that means we have to remove all of this material. We have to remove. Okay, We know the initial dimensions of the workpiece. It's a known value. Then the geometry should obtain, we know the dimensions. So then we can calculate this volume. If we know this volume and if we know this value, we can directly estimate total energy for this to manufacture this component. Okay, that is why we are calculating specific energy of material removed. I think you all more clear with this 2019 exam paper question. Okay, then if you have any doubt, you can put into a comment section. Then I will give the 2020 exam paper question as the class test. Okay, I will send that through email. The submit before I will give the deadline. Then submit the 2019 paper question as a class test. Okay, thank you. Let's continue on next day class.